All right, problem number 2, which is a nice application of scalar line integrals, asks us to find the average value of the temperature function t of xy, which is equal to 10 minus x squared minus 2y squared over the boundary of the disk d, whose radius is 5 and its center is at the origin. So here's our disk d, and I'll refer to the boundary of this disk, which is just the circle of radius 5 centered at the origin, as c. And we want to find the average temperature along this boundary circle. Okay, so just as we found the average temperature throughout a region using a double integral, recall that we just took the double integral of our temperature function over the region and then we divided by the area of the region. Well, by the same reasoning, the average temperature over a curve is going to be 1 over the length of that curve times the line integral of our temperature function over that curve. Okay, so we're going to need a parameterization for the curve. And so given that C is just a circle here, it's the circle of radius 5 centered at the origin, I can parameterize this as 5 cosine t, 5 sine t, and that's going to give us a counterclockwise parameterization. And to make one trip around the circle, we're going to let t vary from 0 to 2 pi. Okay. So now let's go ahead and set up this line integral. Okay, so the temperature function evaluated along the curve C, right, is just simply found by plugging in 5 cosine t for x and 5 sine t for y, and that's going to give us 10 minus 25 cosine squared t minus 50 sine squared t. And then for our differential arc length, ds, well, that's just going to be equal to the magnitude of the derivative of our vector function r describing this path times dt. And so I've gone ahead and computed that, and we just get 5 dt, which is quite nice. Our integral is going to be from 0 to 2 pi. Those are our bounds as we make one trek around this circle. And then out in front, I have just 1 over the length of the circle, and it's a circle of radius 5, so just the length is given by the circumference, right? So 10 pi there. Okay, cool. So now let's go ahead and compute this. And the first thing I recommend doing, since you have a combination of cosine and sine terms, here I've just traded in sine squared for 1 minus cosine squared. Okay, and then when you open up parentheses and combine like terms, you wind up just getting minus 40 plus 25 cos squared, which is quite a bit simpler. Then we're going to use that half angle identity. It says that cosine squared of t is equal to 1 plus cos 2t all divided by 2. Okay, so if you replace cos squared with this expression, okay, you're going to wind up, after doing a little bit of cleaning up, minus 55 halves plus 25 halves times the cosine of 2t. Okay, so now if you integrate from 0 to 2 pi, for this constant part, you just get minus 55 halves times the length of this interval, which is just 2 pi. And then here you're going to get a sine 2t divided by 2, and it'll multiply the 25 halves to give you a 25 fourths out in front, and then the sine of 2t. And notice when you evaluate from 0 to 2 pi, okay, this expression is 0 at both of those bounds. So this whole thing just drops out. And then you have that 1 over 2 pi out in front. Keep in mind that this 5 that came from the differential arc length element, ds, if you pull that in front, then you get 5 over 10 pi, simplifies to 1 over 2 pi. And now these 2 pi's are going to drop out, and so you get this average temperature over this boundary circle to be minus 55 over 2. Now there aren't units here, but whether it's, say, Fahrenheit or Celsius, pretty darn cold. All right, great. That's going to do it. Thanks.